October 2nd, 2025. On the surface of Mars, beneath a cold and silent sky, the Perseverance rover was taking a series of night sky calibration images. Nothing unusual, just another set of raw frames meant to measure the movement of distant stars. Then buried in that routine data, something appeared. A brief sharp flash of green light, and then it was gone. An amateur astrophotographer named Stefan Burns was the first to notice. He wasn't looking for anything extraordinary. He was simply downloading and stacking the publicly available images that NASA releases every day. 9 minutes of data compressed into a single time-lapse. But when the stars began to drift smoothly across the Martian sky, one bright streak cut across their motion at an impossible angle. It wasn't a cosmic ray, it wasn't a sensor glitch, it was something moving fast. 60 kilometers per second, twice the orbital speed of Earth, faster than almost anything in our solar system. Burns paused, the frames adjusted, the contrast ran the alignment again. The object was real, and it wasn't behaving like a comet, an asteroid, or any known satellite. Within hours, he posted the clip online. Astronomers and enthusiasts around the world began to replay it frame by frame. Some saw a single point of light. Others swore there were several darting together across the void like a small formation. By the next morning, forums were filled with screenshots, overlays, calculations. The timestamp matched the predicted moment when an interstellar object called 3I Atlas would pass near Mars close enough for multiple orbiters to have it in view. The coincidence was too perfect to ignore, but if those streaks of light were truly 3I Atlas, then it was moving in a way that defied expectation. The trajectory wasn't steady, the glow was the wrong colour, and the faint green hue spreading across the frame suggested something chemical, something active. On Earth, green light usually means oxygen, copper, or dicarbon, the two-atom carbon molecule that flares when sunlight excites it. Many comets turn green because of that simple reaction. But 3I Atlas is not an ordinary comet. Spectroscopy shows that it lacks the very carbon chains that make such light possible. In theory, it should be colourless pale, even invisible against the starfield. Yet here it was bright and unmistakably emerald. For scientists, anomalies like this are puzzles waiting to be solved. For everyone else, they are the spark of wonder, and sometimes unease. The Mars data was supposed to be routine, a test of instruments. Instead, it had become the beginning of a mystery. Stefan Burns wasn't the only one watching. In the days that followed, other users analysed the same raw images. They corrected for Mars's rotation, stabilised the starfield, and found faint trails parallel to the first. Not one object, but several, each moving at slightly different speeds. Could they be fragments, background asteroid, or was the camera catching something else, something accompanying the main body of 3I Atlas as it swept past the red planet? NASA said little. The official archives showed that multiple orbiters, Mars Reconnaissance Orbiter, ExoMars Trace Gas Orbiter, Mars Express, had all been scheduled to observe the same region of sky. High-resolution instruments capable of resolving features tens of kilometers wide were pointed directly at the object, yet none of those images appeared in public databases. For now, there was only silence and a growing sense that something unusual had happened above Mars. From the beginning, 3 Atlas has been an enigma. It is the third known interstellar object ever detected passing through our solar system, a traveller from another star. Scientists expected it to be strange, different composition, unfamiliar behaviour, but not impossible. And yet one by one it has broken nearly every rule we thought we understood about comets. Its chemistry doesn't match, its motion is too steady, its light too green. Burns's discovery was small, just a few frames of data, but it reignited a question that runs deeper than science. We spend our lives looking outward, building machines to see farther, sharper, clearer. But every now and then something looks back. Something crosses the thin boundary between curiosity and fear, reminding us how little control we have over the unknown. As the images from Mars fade to black, only one thought lingers. We thought we were observing the universe. But what if for a brief moment on an alien world the universe was observing us? It glows like a comet. but the chemistry says it shouldn't. When 3I Atlas first appeared in telescopic images, the colour was unmistakable, a brilliant green halo surrounding a pale core, visible even from amateur telescopes under dark skies. It was beautiful, hypnotic, and deeply confusing. Comets turn green all the time. We understand the physics of it completely. When sunlight hits the gas surrounding a comet, it excites molecules called diatomic carbon, two carbon atoms bound together. Those molecules absorb ultraviolet light and release it again in the visible spectrum, creating that vivid emerald glow. Its chemistry is predictable as sunrise, but 3I Atlas refuses to play by those rules. The European Southern Observatory's very large telescope, the Hubble. Space. Telescope and other observatories have all pointed their instruments at it. The results were consistent and perplexing. The comet's coma, the fuzzy halo of gas that surrounds it, contains almost no diatomic carbon at all. The spectral lines that should be bright and sharp in that region of the spectrum are missing. It is what astronomers call chain-depleted. In other words, the molecules that make comets glow green are simply not there. So why is it glowing? The first idea was that it must be a different gas. The most obvious candidate is carbon dioxide. 3I Atlas is filled with it far more than any comet we've seen before. CO2 is carbon bonded to oxygen, and it can make an object extremely bright when sunlight reflects off it. But brightness is not colour. Carbon dioxide produces white light, not green. And there's another strange detail. The ratio of CO2 to water in 3I Atlas is completely inverted. Typical comets have far more water vapour than carbon dioxide. In 3I Atlas, it's the opposite. It is by every metric chemically upside down. Scientists began to explore other possibilities. Could the colour come from excited oxygen, as in an aurora? Perhaps, but that would require powerful magnetic fields or strong solar wind interactions, none of which have been detected around the object. Could it be the reflection of sunlight off metallic dust maybe, but the spectrum doesn't match? Nickel and iron can produce emission lines, but not the wide green band seen here. Whatever is causing the light, it's happening at a molecular level we don't yet understand. One researcher described it as a chemical paradox in motion, an object that obeys the laws of physics but ignores our expectations. In the history of astronomy, that's not uncommon. Many discoveries begin as anomalies that force us to rewrite the rules. Still, this one feels different. The data keeps pointing towards something that should not exist. As the object approaches the sun, it should be heating up, shedding gas, evolving in predictable ways. But its spectrum remains stubbornly consistent. No matter how bright it gets, no matter how much it changes shape, that same impossible green persists. It's as if the colour is built into the object itself, not a product of sunlight or chemistry, but a property of whatever it's made of. Some astronomers have joked that maybe the explanation is simpler. Maybe it's aliens. Maybe they just like green lights. Humour is often how scientists deal with mystery. Beneath the laughter, though, is a growing realization that 3I Atlas is not just another comet passing through. It's a visitor that carries information about how matter behaves under conditions we've never seen before. The absence of diatomic carbon means that the familiar pathways of comet chemistry are missing. The presence of abundant CO2 suggests a composition forged in an environment far colder or older than anything in our solar system. Some models place its birth around a red dwarf star where low ultraviolet radiation would allow unusual molecules to survive. Others imagine a system where carbon was bound up in exotic ices or metals long before the comet was ejected into interstellar space. Every scenario stretches what we think we know about planetary formation. Meanwhile, ground-based observatories continue to watch the green halo as it changes shape and brightness. Some nights it appears diffuse and ghostly. Other nights it sharpens into a compact sphere. The fluctuations could be caused by rotation jets of gas or something else entirely. For now, every explanation remains provisional. The data says one thing, the colour says another, it glows like a comet. But the chemistry says it shouldn't. And in that contradiction lies the essence of discovery. The universe is under no obligation to behave the way we expect it to, it simply shows us what is. All we can do is look closer, measure better, and keep asking why. When Stefan Burns released his time-lapse of the Perseverance sky images, most people saw only one strange streak of light racing across the Martian sky, but not everyone agreed. Within hours, a new voice joined the growing conversation online, a user who went by the name Naktaf, a German astrophotography enthusiast who called himself the Night Monkey. He claimed that Burns hadn't captured a single object at all. He had caught several. Using open-source software, Naktaf stabilized the star field corrected for Mars's slow rotation and subtracted the expected motion of background stars. The process eliminated noise and cosmic rays, leaving only the moving sources of light. When he replayed the sequence, a second faint dot appeared, moving just slightly behind the first. Then a third, even dimmer, following at a different angle. They weren't artifacts or lens flares. They were coherent, persistent, and they seemed to share the same trajectory. Soon others began repeating his method, layering multiple datasets from NASA's raw archive. Some used AI-based motion tracking to highlight transient objects. The results were unsettlingly consistent. At least 2, possibly 3 separate points of light moved together across the frame, each at roughly the same velocity. If these were parts of a single object, they were travelling in formation, maintaining distance over millions of kilometres. If they weren't, then Mars had just been brushed by something far more complex than a solitary comet. In online forums and amateur observatories, theories multiplied. Could this be a fragmenting comet splitting under solar stress? Maybe smaller chunks had broken free and were reflecting sunlight differently. Fragmentation happens. Comets are fragile, but the spacing looked too deliberate, too stable, and the light curves were almost identical. One observer compared the pattern to a convoy rather than a debris field. Professional astronomers took notice, but they remained cautious. The human eye is easily fooled by digital noise, by the way stacked images amplify faint variations. To test the claim, independent researchers began comparing the Perseverance data with simultaneous captures from orbit. On October the 2nd and 3rd, multiple spacecraft were watching the same sky. The Mars Reconnaissance Orbiter's HiRISE camera had been tasked with imaging 3I Atlas. The ExoMars Trace Gas Orbiter and ESA's Mars Express were also scheduled to observe during the flyby window. These weren't casual snapshots. They were coordinated, high-priority campaigns designed to record the closest look ever taken at an interstellar object. Each camera had its own strengths. HiRISE could resolve features down to 30 centimeters on the Martian surface. At 29 million kilometers away, that translates to about 30 kilometers per pixel, still precise enough to distinguish between a single nucleus and multiple fragments. The Trace Gas Orbiter's color imager could detect subtle differences in composition. Mars Express could capture depth and structure through stereo imaging. Together, the three should have provided a complete picture of 3I Atlas as it passed. But none of their images have been released. NASA's official statement was brief. The Mars orbiters conducted their observations successfully. Data processing was underway. Updates would be provided after calibration. Then nothing. Days passed. The public databases that usually fill with new images every 4 hours stayed quiet. The community that tracks these updates noticed immediately. ESA, which operates under its own protocols, also went silent. For an observation of this significance, the absence of even a single preview frame felt deliberate. Meanwhile, the amateur network kept working. Burns's video became a kind of digital Rorschach test. Some viewers saw fragments, others saw tricks of light. Analysts pointed out that if multiple objects were really present, they would each have slightly different motion due to parallax, as Mars rotated beneath them. Those differences, faint but measurable, were visible in the stacked frames. At least 2 tracks diverged by a few pixels, small but statistically significant. If true, the implications were profound. Multiple components could mean a natural breakup or something more organized, a cluster, a system, or a body accompanied by smaller companions. In celestial mechanics, the idea isn't impossible. Binary asteroids exist. Even comets can have fragments that travel together. But this was an interstellar visitor moving at 60 kilometers per second, crossing the solar system from beyond our star's influence. The precision of its movement defied expectation. Scientists who reviewed the claims tried to keep perspective. Without the official data from orbit, it was all speculation. Yet the timing of the silence only deepened the mystery. On October 3rd, every major instrument around Mars was pointed at the same patch of sky. They all observed. They all recorded. And then, silence. The data never came. In science, silence can mean caution or confusion. Under normal circumstances, when a spacecraft captures something new, the images appear almost immediately. NASA's public databases update within hours. Raw frames, calibration files, instrument readouts, they all flow through a process that has been refined over decades. It starts on Mars, where orbiters like the Mars Reconnaissance Orbiter or the ExoMars Trace Gas Orbiter store their data on board, then transmit it back to Earth through scheduled communication windows. From there, the information moves through deep space networks, is received by ground stations, unpacked, and passed through a series of automated pipelines. The images are geometrically corrected, color balanced, and filtered for noise. Once verified, they are posted online for scientists and the public to access. The whole process usually takes less than a day. Even for complex data sets, the delay rarely exceeds 24 hours. But after October 3rd, that rhythm stopped. The Mars orbiters had just completed their coordinated observation of 3I Atlas. Every camera that could be pointed at the sky was watching, from the HiRISE instrument on MRO to ESA's Trace Gas Orbiter and Mars Express. The observation window was short, 3 hours at most, but enough to capture the closest look humanity had ever had of an interstellar object passing near another planet. Then the data should have flowed. It didn't. At first, no one thought much of it. Delays happen. The data has to be cleaned, calibrated, aligned. But 48 hours passed, then 72, still nothing. Amateur astronomers checking NASA's public repositories noticed the gap before anyone made an announcement. The last update was a routine surface image from Perseverance. The sky frames the orbital captures the spectral data all missing. It was as if Mars had gone dark. The official explanation was simple. Data processing is underway. That's all the agency said. But within the planetary science community, questions began to circulate. The data pipeline for these missions is transparent, efficient, and highly automated. Nothing short of a deliberate hold or a serious system failure could explain a total blackout lasting days. There were no reports of system failures. To understand what might have happened, it helps to know how delicate these observations are. The cameras on Mars orbiters aren't designed to track fast-moving targets against a starfield. Their normal job is to photograph the surface of Mars terrain, craters, dust storms. When they point into deep space, the calibration changes completely. They have to adjust for brightness, for motion blur, for the relative position of the spacecraft. Any slight miscalibration can produce ghost images or false signals. Before such data can be released, it must be checked frame by frame. Otherwise, an optical glitch could be mistaken for something real. Caution is standard procedure, but some researchers quietly suggested that this delay felt different. The instruments hadn't failed, they had succeeded too well. If something unexpected appeared, something hard to categorize, it could trigger an internal review. Images showing anomalies often go through additional verification. Scientists want to be sure they're not looking at sensor artifacts or cosmic ray hits before publishing anything that might fuel public speculation. That process can take days, sometimes weeks. The more surprising the result, the longer the silence. There was another factor, less technical and more human. Around the same time, budget restrictions and administrative changes were slowing data release protocols across several NASA divisions. Staffing shortages meant fewer people on the review teams. Priority systems were reshuffled. When every image requires sign-off from multiple reviewers, a slowdown in bureaucracy can feel like secrecy. At the European Space Agency, the structure is different, but the result was the same. ESA's Mars Express and ExoMars images didn't appear either. Two independent agencies, two separate data pipelines, both quiet. Coincidence, possibly. Coordination, maybe. It wouldn't be the first time agencies decided to synchronize their announcements for clarity. But in the world of open science, any coordinated silence looks suspicious. While the official channels stayed quiet, one independent researcher stepped forward, Simeon Schmaus, a planetary image analyst known in the amateur community for his precision and persistence. He had been processing raw Perseverance data for years, creating stabilized mosaics and time-lapse videos that often revealed subtle details missed in the initial releases. On October the 1st, a day before Burns's discovery, he posted a thread on social media claiming to have seen an early trace of 3I Atlas in the rover's sky frames, barely visible but distinct from the background stars. The object's motion, he said, didn't match the predicted trajectory. It was slightly off by just enough to notice. Then abruptly he stopped posting. No retraction, no clarifications, no updates. His account went silent. For someone as active as Schmaus, it was unusual. He'd built a reputation on transparency, sharing every step of his process, every filter, every calibration parameter. His disappearance left a vacuum. People began to wonder, had he found something that required confirmation, or had someone asked him to wait? Inside NASA and ESA verification teams were still at work checking the data. The HiRISE instrument collects across 3 color bands, blue, green, and near-infrared. The Trace Gas Orbiter's color imager detects variations as small as a few percent in reflectivity. If those instruments captured anything out of the ordinary, an unexpected glow, a fragment, a pattern of motion, it would need cross-validation before release. Each frame would be scrutinized for artifacts, each anomaly compared with star charts, cosmic ray databases, and known background objects. That kind of analysis isn't instant, but it rarely takes weeks, and yet the silence stretched on. Within the broader community, the speculation split into 2 camps. One group argued that the delay was purely procedural. When an object behaves unpredictably, scientists must double-check every assumption before presenting results. The other group suspected something more deliberate. The timing of the blackout right after the closest approach of an interstellar object was too perfect to dismiss. In their view, the agencies weren't verifying. They were deciding what to say. The truth probably lies somewhere between caution and confusion. When faced with the unexpected, even the most transparent institutions move slowly. Every discovery passes through layers of verification bureaucracy and narrative control. The higher the stakes, the thicker the layers. And 3I Atlas carries more weight than most. It's not just a comet, it's a messenger from another star system crossing our own at an angle that invites scrutiny. Every new image, every spectrum, every data point reshapes our understanding of what interstellar objects can be. If any of that data contained something unexplained, a structure, an emission, a reflection, then the people in charge of releasing it would know they were about to start a global conversation, maybe even a global argument. And so for now, the silence remains. The data exists. Somewhere in the archives of NASA and ESA, the October 3rd observations are being studied, calibrated, debated. The world waits for a glimpse of what those orbiters saw. But the longer the delay grows, the more the questions multiply. Did the instruments capture multiple objects? Did they record the green flash seen from the Martian surface? Did they find something that doesn't fit into any known category? Or, as some quietly wonder, did Simeon Schmaus see something real before the rest of us, and was he asked to wait? On a summer night in 1977, a radio telescope in Ohio heard something it wasn't supposed to. It was called the Big Ear, a giant immobile array of aluminum panels listening quietly to the sky. Its purpose was simple: to hunt for narrowband radio signals, the kind that nature rarely produces, but technology often does. At 10:16 p.m. on August 15th, the printer connected to Big Ear began spitting out a string of numbers and letters, intensity readings of radio noise from deep space. Then in the middle of the routine printout, a burst appeared. The sequence 6EQJ5. It lasted 72 seconds, far longer than any random spike of interference and far stronger than anything the telescope had recorded before. The signal came from a fixed point in the constellation Sagittarius, and when astronomer Jerry Eman circled it on the paper, he wrote one word in the margin: "Wow." That simple exclamation gave the signal its name and its mystery, because in nearly 50 years since, we've never heard anything like it again. The WOW signal was narrowband, meaning it was confined to a razor-thin range of frequencies. Natural sources, Stars, quasars, pulsars broadcast wide, noisy spectra. Technology, by contrast, produces focused signals, efficient and precise. The WOW signal sat at 1420 MHz, almost exactly the frequency of what physicists call the hydrogen line. Hydrogen, the most abundant element in the universe, emits radio energy at this frequency when its atoms flip their spin orientation. It's a natural frequency, but also a meaningful one. For decades, scientists have speculated that if another civilization wanted to send a message that any intelligent species could recognize, they would choose the hydrogen line. It's the same everywhere. It's the one universal channel all advanced observers would understand. So when Big Ear heard a 1420 MHz beacon from deep space, astronomers had to consider the possibility it might not be natural. For years they searched for a repeat, scanning the same patch of sky hundreds of times. Nothing. No echo, no pulse, no follow-up. The source was gone. All we knew was that it came from somewhere in Sagittarius, and then the world moved on, until now. When the interstellar object 3I Atlas was discovered, its trajectory was traced backward through planetary perturbations, through gravitational influences, until it intersected with the outer regions of our solar system almost half a century ago. The math was tedious but precise. Avi Loeb, an astrophysicist from Harvard, plotted the object's path in reverse, accounting for solar wind velocity decay and the bending of light. His conclusion stunned everyone who saw it. In August of 1977, at the exact time the Big Ear telescope recorded the WOW signal 3I Atlas, would have been far beyond Pluto, around 600 astronomical units away, still bound toward the Sun. And more importantly, from Earth's perspective, it would have been in the same general direction of the sky, Sagittarius. The alignment wasn't perfect. Nothing in space ever is, but the coordinates were close enough to raise eyebrows. The separation between the two directions, 8 degrees of right ascension, 9 degrees of declination. In human terms, the size of a clenched fist held at arm's length. The odds of two random events in the sky aligning that closely, around 0.6%, less than 1 in 100. On its own, that number doesn't prove anything, but it's enough to make you look twice. If 3I Atlas had already entered the outer solar system by 1977, then it wasn't a visitor, it was already here. Which raises an unsettling question: could the WOW signal have been a transmission announcing its arrival? To explore that, we need to look at the power of the signal itself. The Big Ear recorded an intensity between 54 and 212 Janskys. For comparison, the Sun, when measured in radio at that frequency, sits in the same range if you were standing much closer to it. For something originating hundreds of billions of kilometers away, the power output would have been immense. At 600 astronomical units, a source would need to emit between half a gigawatt and 2 gigawatts of power to produce what Big Ear detected. That's roughly the energy of a single nuclear reactor. Enormous by human standards, but well within reach for a civilization capable of crossing interstellar space. And then there's the detail everyone overlooks: the frequency shift. The WOW signal wasn't exactly at 1420 405 Mets. It was slightly higher, 1420 446. That's a blue shift, meaning the source was moving toward Earth. When Loeb ran the numbers, 3I Atlas's velocity, around 60 kilometers per second inbound, produced almost exactly the same blue shift in frequency. The correlation wasn't perfect, but the match was close enough to fall within observational error. The pieces were starting to fit together, at least loosely. The trajectory, the direction, the frequency, the power, all of them whispering the same improbable story. Of course, the scientific community reacted with caution. There are natural explanations for the WOW signal. It could have been a reflection from space debris, a transient planetary emission, even a satellite signal that slipped through filters. But every attempt to reproduce those conditions has failed. The silence since that night has been total. If the signal was artificial, then it was a one-time transmission, 72 seconds of focused energy sweeping across Earth's rotation window, captured by accident, then gone forever. Which brings us back to 3I Atlas. When it reappeared this year, glowing green in the night sky, the parallels became impossible to ignore. the third interstellar object ever found, the same general region of origin, a velocity consistent with that ancient signal's Doppler shift. It's almost poetic, as if something sent us a postcard in 1977 and only now has the sender arrived. Could that be true? Probably not. But it also hasn't been proven false. Skeptics point out that even if the alignment is real, it doesn't imply causation. Space is vast, coincidences happen. The WOW signal could have come from a distant star and 3i Atlas could simply share its line of sight. But Loeb's calculations have a way of making coincidences uncomfortable. They force us to ask questions we'd rather leave alone. What if the WOW signal wasn't a call from a distant civilization at all, but a local transmission? Something already in our solar system broadcasting briefly before falling silent. What if 48 years ago a visitor announced itself in the only universal language it knew? Physics will never know for sure. The Big Ear was dismantled decades ago. The original equipment is gone. The raw analog data was discarded. All that remains are the printouts, the circled number, the handwritten word, WOW. And yet the mystery endures. Every few years someone rediscovers it. A new telescope listens. A new algorithm searches the noise, but no one hears anything. The channel stays empty. Now, as 3i Atlas moves behind the sun beyond the reach of our instruments, we find ourselves listening again not with antennas but with imagination. The green glow, the strange chemistry, the improbable trajectory, the silent approach. Each anomaly alone could be coincidence. Together they start to sound like a pattern. If the WOW signal was a message, it was simple. A single note, pure and clear, broadcast at the universal frequency of hydrogen, the building block of everything. It said, in effect, we are here. 48 years later, something is. It hasn't been proven true, but it hasn't been proven false either. When the first spectra of 3i Atlas were published, the initial results seemed ordinary. Reflected sunlight, traces of gas and dust, nothing out of place. But then came a surprise buried deep in the data, the unmistakable fingerprints of nickel. Nickel is not unusual in space. It's a common byproduct of stellar evolution and can be found in asteroids, meteorites, and cometary dust. On Earth, it's usually bonded with iron, the two metals forming stable alloys that build the cores of planets and the hearts of machines. In nature, nickel never travels alone. Wherever there is nickel, there is iron. Except here. The European Southern Observatory's Very Large Telescope detected nickel emission lines, bright clear and distinct, radiating from the coma of 3i Atlas. Yet the corresponding lines of iron were missing. Astronomers ran the numbers again and again, but the pattern held. The ratio was inverted. In the gaseous cloud surrounding the comet, nickel was abundant. Iron was almost non-existent. Based on the intensity of the spectral lines the object was shedding, about 5 grams of nickel every second into space, an invisible vapor trail of metal atoms. That might not sound like much, but at cosmic scales it's extraordinary. For nickel to be vaporized and escape into the coma, the temperature near the surface of 3i Atlas would need to exceed 1,000 degrees Celsius. Natural comets can reach those temperatures when they dive close to the sun. 3i. Atlas, however, was still between Mars and Jupiter, far too cold for metal to sublimate. Something didn't add up. On Earth, separating nickel from iron is difficult. They bond tightly in ore, and refining them requires heat pressure and chemistry. One of the key methods is the bond process, a technique used in metallurgy to produce ultra-pure nickel. It involves creating a gas compound called nickel tetracarbonyl. Nickel atoms bonded with carbon monoxide molecules. The compound forms only under specific conditions: moderate temperature, low pressure, and an abundance of carbon monoxide. When heated, it breaks apart again, releasing pure nickel vapor while leaving iron behind. It's an elegant reaction, and it's almost exactly what seems to be happening on 3i Atlas. The coma is full of carbon dioxide and trace carbon monoxide. The environment matches the ingredients for nickel tetracarbonyl formation. As the sun's weak radiation warms the surface, the compound could decompose, releasing nickel gas while keeping iron locked in solid form. If that's the case, then the chemistry of 3i Atlas isn't random, it's industrial. It's a system that mimics human engineering occurring naturally or not. In nature, nickel never travels alone. In industry, it often does. For some scientists, this discovery was an opportunity to learn something new about planetary chemistry. Maybe there are natural environments in deep space where the conditions for these reactions exist. Maybe under the right combination of elements, nickel can decouple from iron without any artificial help. It would be a revelation proof that processes we once thought unique to human technology could occur spontaneously among the stars. But not everyone was convinced. Avi Loeb, whose theories often sit at the edge of mainstream science, proposed a different possibility. He suggested that the nickel emissions might come not from the object's interior but from its surface. A metallic coating, he called it an outer layer, made of high nickel alloy that was slowly eroding as 3I Atlas travelled through space. As sunlight struck the surface, it would heat and ablate the metal, releasing atoms of nickel into the coma. If that were true, it would explain both the purity of the nickel and the absence of iron. High nickel alloys are prized in spacecraft construction because of their resistance to heat and corrosion. They survive where ordinary materials fail. Either nature just taught us new chemistry, Loeb said, or someone already knew it. It's a provocative statement, the kind that divides the scientific community. Most researchers prefer simpler answers: unknown natural processes, unseen variables, coincidences. Yet even the skeptics admit that the nickel anomaly is difficult to dismiss. The emission lines are clear. The data has been verified independently by multiple observatories. Whatever is happening on or around 3I Atlas, it's not following the usual rules. To put it in perspective, when comets from our solar system approach the Sun, we sometimes detect traces of vaporized metals. Iron, sodium, magnesium, they appear briefly in the coma, then fade as the comet moves away. But 3I Atlas was radiating nickel long before it entered the inner solar system, long before any known heat source could have triggered sublimation. It was active in the cold, deep regions between Mars and Jupiter, glowing with the spectral signature of a furnace that shouldn't exist. Some have suggested that the nickel might come from within the comet itself, from radioactive decay or exotic minerals breaking down over time, but that would produce a mix of elements, not a clean nickel signature. Others propose micrometeorite impacts or electrical discharges from the solar wind. Yet those mechanisms can't account for the steady, consistent output measured over months of observation. It's as if something on 3I Atlas is regulating the release, precise, controlled, continuous. For those willing to speculate, that raises uncomfortable possibilities. If the surface truly is coated in an engineered alloy, then 3I Atlas might not be a comet at all. It might be a shell, a vessel, or a fragment of something designed. But that's a leap too far for most scientists. Without physical samples, without direct images, it's only a story written in light. Still light tells the truth. The spectrum doesn't lie. The green glow that first drew attention to 3I Atlas may not come from gas or dust, but from metal vapor scattering sunlight. The chemistry of its coma resembles that of industrial exhaust. The absence of iron, the abundance of nickel, the persistent emissions all point to a process both familiar and alien. Maybe this is how the universe builds. Maybe in some far-off system the conditions exist naturally to refine metals in ways we've only learned through technology. Or maybe, just maybe, we're seeing the remains of something built with purpose. As 3I Atlas moves closer to the Sun, its nickel trail continues to grow. Spectrometers track the shimmering plume as it expands and fades into interplanetary space. Every second, another 5 grams of pure nickel are lost forever. Whether it's a natural reaction or the echo of a design, the effect is the same, a silent metallic whisper crossing the void. For now, the mystery endures. The universe is filled with metals, but rarely in this form, rarely so pure. If this is chemistry, it's chemistry we don't yet understand, and if it's not, then perhaps the question isn't about the elements at all, but about who or what put them there. For as long as we've watched them, comets have behaved the same way. When they approach the Sun, their icy surfaces warm and begin to vaporize, releasing gas and dust that stream outward, always away from the light. The solar wind blows this material into the long, graceful tails we see arcing across the sky, brilliant banners of sublimation and sunlight. It's one of the simplest and most predictable rules in planetary science. A comet's tail always points away from the Sun. But 3I Atlas decided to ignore that rule too. In mid-September, as the object drifted between Mars and the inner solar system, the Hubble Space Telescope turned its gaze toward it. The image it captured stunned astronomers. Instead of a single tail streaming away from the Sun, 3I Atlas displayed a faint jet of material pointing toward it, a narrow plume of reflected light extending in the wrong direction. It was subtle but unmistakable. The so-called anti-tail. At first, many assumed it was an illusion, a trick of perspective. After all, the geometry of space can deceive the eye. A comet's orbit isn't a flat line but a curve in 3 dimensions. From Earth's viewpoint, depending on the angle, the tail can appear to bend even reverse direction. That happens occasionally when a comet passes between the Sun and the observer. The thin sheet of dust viewed edge-on can create a false impression that the tail is pointing the wrong way. But the measurements from Hubble didn't fit that explanation. The viewing angle was shallow, not edge-on, and the jet's brightness didn't match the diffuse glow of a normal dust sheet. This was a focused, narrow feature, something active, not passive. The light reflected off it oscillated in intensity over time as if the jet itself was pulsing. Astronomers began searching for a physical explanation. One possibility was the presence of ultrafine dust particles far smaller than those emitted by typical comets. Microscopic grains can behave unpredictably under solar radiation. Instead of being pushed away by light pressure, some can be drawn sunward for brief periods before the wind overwhelms them. If 3I Atlas was shedding unusually small dust nanometer scale fragments, the effect might mimic an anti-tail. It's rare, but it can happen. The second hypothesis was more dynamic. Perhaps the plume wasn't dust at all, but gas. Jets of vaporized material can erupt from specific vents on a comet's surface. If one of those vents happened to face the Sun, and if the gas was dense enough, it could form a visible forward jet. In that case, the anti-tail wouldn't really be an inversion of direction, but an expression of geometry, the same natural process seen from an unusual perspective. And then there was a third, more provocative idea. What if the forward jet wasn't a product of sunlight or pressure, but a form of propulsion? To be clear, no one is claiming 3I Atlas has engines. But the motion of the object complicates the story. While most comets experience small erratic changes in speed and direction caused by the push of their own outgassing, 3I Atlas has remained remarkably stable. Its non-gravitational acceleration is among the lowest ever recorded. The jet, if it's real, isn't altering its path the way natural jets should. It's there, it's visible, but it isn't pushing the comet around. That's when Avi Loeb raised an unsettling analogy. Maybe the jet isn't thrust, caused by random heating but controlled braking, a form of deceleration. It looks less like a comet tail, he wrote, and more like thrust. If that sounds extraordinary, remember that in physics thrust is simply directed momentum, matter expelled in a specific direction. A spacecraft slows down by firing engines forward against its motion. Theoretically, an object with the right orientation and energy source could produce a similar effect, releasing mass toward the Sun to resist acceleration. It's a maneuver familiar to engineers, not astronomers. Of course, there are natural ways to mimic that behavior. If 3I Atlas's spin axis is tilted just so a vent could be releasing material directly along the sunward vector, over time that outflow would appear as a steady anti-tail even if the process were entirely random. The problem is persistence. Most cometary jets flicker and die within days as the surface evolves. The sunward plume of 3I Atlas has lasted for months. Hubble's follow-up images only deepened the puzzle. The forward jet brightened slightly as the object neared perihelion, then stabilized, refusing to fade. Spectral analysis revealed a faint metallic sheen in the reflected light nickel, again consistent with what ground-based telescopes were already seeing in the gas spectrum. Whatever the jet was, it was carrying metal with it. For planetary scientists, that detail was almost too much. A comet emitting metallic vapor is rare enough. A comet emitting metallic vapor toward the Sun was unprecedented. The combination suggested an organized process, or at least one that wasn't purely chaotic. Still, the community resisted sensational conclusions. They searched for better models. Some turned to electrostatic forces, the interaction between charged dust particles and the solar wind. Others modelled the possibility of a double nucleus, where one fragment's shadow altered the outflow of another, creating a false sense of reversal. A few even proposed that 3I Atlas was surrounded by a cloud of companion debris, forming a temporary disk that could scatter sunlight forward. Each theory solved part of the mystery, but none solved it all. Meanwhile, the anti-tale continued to evolve. In late October, astronomers tracking the object from Chile reported a new feature, a secondary plume forming at a right angle to the first. For the first time, 3I Atlas looked less like a comet and more like a machine. Two opposing jets, symmetrical and steady. The data wasn't conclusive, but the image was haunting, a glowing green nucleus flanked by lines of faint silver light stretching across millions of kilometers. Even the most cautious scientists admitted they had never seen anything like it. In interviews, they chose their words carefully. Active jets, unusual geometry, highly anisotropic outgassing. Technical phrases that mean one thing: we don't know what's happening. Whatever the cause, the effect is clear. 3I Atlas is interacting with sunlight and matter in ways no other comet has. Its metallic composition, its near-perfect trajectory, and now its sunward jet all point to an object operating under a different set of physical rules, or at least a different balance of forces. Some see it as proof that our models of cometary physics are incomplete. Others see it as a sign of intention of design. For now, both explanations remain on the table. Hubble's final image of the season shows the forward jet still burning faintly, a slender filament glowing green against the blackness of space. From millions of kilometers away, it's impossible to tell whether the light is a plume of dust or the wake of something moving with purpose. But the picture lingers unsettling and unforgettable. It looks less like a comet tail, and more like thrust. When 3I Atlas was first detected, astronomers assumed it would be small. Interstellar visitors by their nature are expected to be fragment shards of rock or ice thrown from distant systems, light enough to be accelerated by cosmic chance and gravity. The first of them, 1I Oumuamua, was barely 200 meters long, thin and tumbling like a leaf. The second, 2I Borisov, was larger but still modest by cosmic standards, roughly a kilometer across the size of a mountain. So when early calculations suggested that 3I Atlas might be far bigger, few believed them. But the numbers didn't lie. As the object approached the inner solar system, astronomers measured its brightness, its reflected light, and the size of the coma that surrounded it. The results were staggering. To produce that level of luminosity, given its distance and composition, 3I Atlas would need a nucleus tens of kilometers wide, an estimated mass of 30 billion metric tons. 33 billion. That's the equivalent of 3 Mount Everests compressed into a single silent traveller. It's not just large, it's unprecedented. According to models of interstellar object frequency, the odds of encountering something that massive passing through our solar system are about 1 in 1,000. The cosmos is full of debris, but large intact bodies are rare. They're gravitationally bound to their home stars and require immense forces to escape. Statistically, we should have seen 1,000 smaller objects before one like this appeared. Instead, 3I Atlas arrived early, massive and moving too steadily to be an accident. The comparisons are stark. Oumuamua, small and fast, tumbled erratically under sunlight pressure. Borisov, icy and unstable, began to fragment as it neared the sun. 3I Atlas, by contrast, glides through space as if nothing touches it. Its non-gravitational acceleration, the tiny push caused by outgassing, barely registers. It's as though the object's mass is anchoring it, resisting every external force. The sheer scale of it dampens motion, smooths irregularities, and keeps its path unnervingly perfect. When you combine that with its unusual chemistry and its strange metallic emissions, a pattern begins to emerge. 3I. Atlas doesn't behave like something natural tossed into space by chance. It behaves like something built for endurance. Of course, science demands restraint. The first rule of interpretation is that extraordinary claims require extraordinary evidence. Maybe the size estimates are wrong. Maybe the albedo, the reflectivity, is higher than expected, meaning the object is smaller and brighter than it looks. Or maybe the opposite, the material is darker, denser, heavier than assumed, exaggerating its apparent mass. Every measurement depends on models and every model can fail, but even allowing for generous error margins, 3i Atlas remains a giant. Observations from Hubble, JWST and ground-based telescopes all converge on the same conclusion. This object is simply too large for its category. The probabilities don't make sense. To explain it naturally, we have to assume that the galaxy is filled with similar giants drifting between stars, vast relics of planetary formation that somehow escape their systems without being shattered. Yet in all our searches, we've seen only 3 such visitors, 3 detections out of billions of possible trajectories. If interstellar giants are truly common, where are the rest? Astronomers ran Monte Carlo simulations to test the likelihood. The results were humbling. Given the known density of stars, the average age of planetary systems, and the rate at which material is ejected into interstellar space, the chance of encountering a 30-kilometer interstellar body within our lifetime is infinitesimal. We shouldn't be seeing this at all, unless something else is happening. Perhaps 3i Atlas isn't the product of random ejection, but of deliberate dynamics. In the cold equations of celestial mechanics, large bodies don't wander. They travel with intent, guided by forces precise enough to overcome the chaos of space. The more stable an orbit, the less likely it is to be an accident. 3i. Atlas's path through the solar system is almost surgical. It threads the gravitational fields of the planets with uncanny precision, avoiding close encounters, gliding through zones of observation as if it knows they exist. Is that pure coincidence? Possibly. Space is vast enough to make coincidences inevitable. But when every new measurement defies probability, even scientists begin to wonder where coincidence ends and pattern begins. Some theorists have suggested that 3i Atlas might not be a single solid body at all, but a cluster, a gravitationally bound collection of smaller fragments travelling together. That would reduce its effective mass while preserving its brightness. Yet the light curve doesn't fluctuate the way a cluster would. It remains smooth, unbroken. Whatever it is, it's solid. Others propose that the mass estimates are skewed by reflective metals on its surface, boosting its luminosity beyond what its true size would warrant. That theory aligns with the nickel emissions already detected, but it opens another problem. How did such metals end up on an interstellar comet in the first place? The more we try to simplify 3i Atlas, the more complicated it becomes. At some point, probability stops being comforting. The more impossible the numbers get, the less likely it is that the universe is simply rolling dice. It's worth remembering that every great leap in science began with an anomaly, something that shouldn't exist but did. Uranus's strange orbit revealed Neptune. The bending of starlight revealed relativity. An electron behaving oddly gave us quantum mechanics. The cosmos reveals its secrets by breaking its own rules. Maybe 3i Atlas is just another broken rule, another hint that our understanding of how the galaxy ejects and scatters matter is incomplete. Or maybe it's something more deliberate, something sent not thrown. For now, the data remains what it is: an object 30 kilometers wide, 33 billion tons of mass moving through the solar system on a trajectory so stable it borders on impossible. The odds say it shouldn't exist, but the telescope says it does. The James Webb Space Telescope was supposed to settle the debate. Point its mirrors at a comet and it will tell you molecule by molecule what the object is made of. With 3i Atlas, it did exactly that, then set the conversation on fire. Webb's near-infrared spectrograph measured the gases venting from the object as it warmed. The signature of water should have dominated. In every catalogue of comets we have water as the backbone of the coma. Carbon dioxide is usually a supporting actor, 10 to 20% by abundance, a faint chorus behind the main line. Not here. In 3i Atlas, carbon dioxide outnumbers water by roughly 8 to 1. By mass, the coma reads as almost all CO2, a small fraction CO and a trace of H2O. It is not a deviation. It is an inversion, an entire chemistry turned upside down. The first reaction among comet scientists was disbelief. Instruments can be fooled by glare, by background, by calibration drift. Webb is different. Its spectra are sharp, its baselines clean. The line strengths were unambiguous. Whatever 3i Atlas is shedding, it is not the standard ice mix of the solar system. Explain it then. That is what science does when reality refuses to match the model. 3 natural possibilities rose to the top. The first points to where the object formed. In protoplanetary disks, temperature falls with distance from the star. At specific radii, different compounds freeze out of the gas and become solid ice. We call these boundaries ice lines. In our own system, water condenses relatively close to the sun carbon dioxide farther out, and carbon monoxide farther still. If 3i Atlas formed near the CO2 ice line in another system, its interior could be saturated with frozen carbon dioxide with comparatively little water locked in. Heat it and the CO2 would boil off first and most, filling the coma with the very signature web observed. This is the simplest story, different nursery, different child. But ice lines are not absolute. Disks mix, particles migrate. Even in CO2-rich regions, water is rarely scarce. To get an 8-to-1 ratio, the object would likely need both an unusual birth zone and an unusual history conditions that reduce water or bury it deep beyond the reach of sunlight. Possible, yes. Common, no. The second explanation looks not to birth, but to time. Between the stars, radiation is relentless. For billions of years, cosmic rays comb through interstellar comets, breaking molecular bonds, knocking atoms out of place, churning the top layers into a chemically altered rind. Water is vulnerable to this kind of processing. CO2 can be more resilient. Over geological eras, you can imagine the outer shell of 3i Atlas being stripped of water and enriched in carbon dioxide. When the object finally approaches a star, the first volatiles to escape are not a true sample of its interior, but the weathered skin it wears. Peel that skin off with continued heating and perhaps the composition would drift back toward normal. The problem is that Webb watched over time and the inversion held. If there is a layered transition from processed crust to pristine interior, we have not yet reached it. Either the rind is deeper than we thought or there is no rind at all. Only a body that is CO2 heavy through and through. The third possibility is accumulation. Interstellar space is not empty. It is a slow rain of dust and ions of carbon-rich grains that drift between stars. An object moving at 60 kilometers per second for eons will collide with that dust and trap some fraction of it. If those grains are skewed towards certain chemistries, organics that devolve to CO and CO2, when heated, then a once ordinary comet might acquire an exotic surface inventory. When sunlight returns, you do not see the original recipe. You see a veneer the galaxy painted on. This too has issues. Accreted mantles are messy. They deliver mixed products and isotopic diversity. Webb's measurements look cleaner than that, less like a collage and more like a design. While composition took center stage, other measurements whispered their own defiance. Polarimetry. The study of how light becomes polarized when it scatters off particles gives astronomers a way to infer grain size, shape and structure in a coma. Most comets follow a predictable curve at small phase angles. The polarization dips slightly negative, then becomes positive and rises with angle. 3i. Atlas bent that curve. It showed unusually strong negative polarization at low angles, with a magnitude that outstrips the solar system database. To get there naturally, you need dust, unlike the familiar porous aggregates, perhaps larger, perhaps smoother, perhaps with refractive properties we do not often see. Or you need light that is not only reflected sunlight. If there is even a hint of prompt emission mixed in molecules fluorescing or metals scattering in particular ways, the polarization can shift into unfamiliar territory. Then there is cyanogen. CN is not rare in comets, but its behavior is usually entwined with other carbon chains. Early spectra of 3i Atlas showed CN present before activity surged, even as other carbon chain bands remained muted. It is like finding smoke without the usual fire. It could point to a reservoir of CN-bearing ices accessible near the surface. It could also point to reaction pathways we do not commonly model, photochemistry catalyzed by trace metals or by radiation-hardened organics that break along unusual lines. Put the threads together, and the picture gets stranger. An interstellar object with a CO2-dominant coma. a dust population that polarizes light in ways our templates do not fit, a cyanogen signal out of step with its chemical cousins. And through it all, the metallic fingerprint that keeps resurfacing in both reflection and emission, suggesting that nickel atoms ride with the gas. Each of these findings can be given a natural frame. Each comes with a paper and a model and a graph that shows how under special conditions the universe could do this by itself. The difficulty is not with the parts, but with the sum. If you embrace the ice line hypothesis, you account for the CO2. If you invoke long radiation exposure, you harden the skin and shift the volatility. If you include interstellar accretion, you explain an unusual surface mix. If you tweak dust growth and compaction, you can push the polarization negative. If you adjust photochemistry around CN, you can get early cyanogen without a chorus of carbon chains. Line them up and 3i Atlas threads the needle of improbabilities again and again. There is another way to read the data the way that makes many astronomers uncomfortable. Suppose the composition is not a coincidence of birth and weathering. Suppose the surface nickel is not a curio of deep time, but a material chosen for reasons of durability. Suppose the forward jet with its metallic sheen is not a quirk of nanograins, but a managed release of mass. In that story, CO2 dominance is not a freak of formation, but a feature and exhaust that remains stable across a range of temperatures and leaves an optical signature you can see from far away. The polarization becomes a diagnostic of engineered grains. Cyanogen becomes a tracer, a byproduct in a fuel cycle we do not yet recognize. Extraordinary claims, extraordinary evidence. We do not have that evidence. What we have are spectra and light curves and polarimetric angles mixed with our own biases and hopes. And yet if the purpose of science is to test the improbable until it breaks, then 3i Atlas is the perfect experiment. Point more instruments, listen across the radio band, wait for it to emerge from behind the sun and see if the chemistry shifts under stress. A natural body will reveal itself with time, a designed one might as well. For now, Webb's data stands as a challenge. It asks us to reconsider the comfortable assumption that interstellar comets are just provincial versions of our own. It reminds us that the galaxy is vast enough to grow ice in ways our backyard never did. It also tempts us with the idea that somewhere chemistry is a language and someone else learned to speak it first. Every rule it breaks has an explanation until you try to explain them all at once. For months, astronomers have been tracking 3i Atlas with precision. Its orbit was calculated, refined and recalculated again until the model reached near perfect certainty. The numbers said it would come no closer to Earth than 2.7 million kilometers at its minimum orbit intersection distance, the MOID, the cosmic near miss that defines safety. 2.7 million kilometers comfortably beyond the Moon's orbit, far enough to pose no threat. On paper, that is the end of the story. But orbits are not static lines. They are predictions built on what we can see. When an object enters from interstellar space, its motion carries uncertainties no one can fully map. Tiny deviations multiply over distance. A single unnoticed release of mass, a jet, a burst, a fragment, can shift the trajectory by thousands of kilometers without ever showing up in early data. So far, 3i Atlas has played by the math. It has followed its predicted path with uncanny stability, the kind that reassures physicists and unnerves everyone else. The problem is that the same precision that makes it predictable also makes it suspect. A natural body that large should wobble. Dust jet solar wind radiation pressure, every force we know, should nudge it slightly off course. Instead, it glides as though it is being guided. To account for that steadiness, one hypothesis has emerged, not sensational but curious. Scientists call it the distributed system hypothesis. The idea is simple: what if 3i Atlas isn't one solid object at all, but a system, a parent body accompanied by smaller components, each following the same path, sharing the same momentum, communicating through gravity or other subtle forces. If such fragments exist, they would be small, faint, and easy to miss. Even the most powerful telescopes would see them only as fluctuations in brightness, tiny blips on a light curve. They could drift a few thousand kilometers apart, perhaps more invisible until they interacted with sunlight or crossed a planet's line of sight. That possibility became harder to ignore after the Mars encounter. In early October, 3I Atlas passed within observational range of the red planet, close enough that the orbiters there could collect high-resolution data. Some analysts now believe Mars was not just a waypoint in the comet's journey, but the first checkpoint, a point of alignment along its route through the inner solar system. The data from that period, still unreleased by NASA and ESA, might hold clues. If 3I Atlas was shedding material or deploying fragments, Mars would have been in the perfect position to see them. A distributed system could leave faint traces in atmospheric readings, small flashes of reflected light or radio echoes in the high-frequency bands that orbiters monitor. So far, none of that has been made public. The geometry is suggestive. From the perspective of Mars 3I Atlas passed nearly head-on moving sunward. The timing coincides with the strange multiple object reports from Perseverance and other Mars-based images. If any small bodies detached along the way, autonomous or not, they would have crossed near the planet's orbit. Perhaps they already have. Perhaps the instruments on Mars have seen them and labelled them as something else. Cosmic rays, debris, artifacts of noise. The distributed system hypothesis doesn't require science fiction. In our own solar system, nature produces complex systems all the time. Binary asteroids dance around each other. Comet fragments travel in loose swarms. Even artificial spacecraft have been launched in clusters that act as one. But with 3I Atlas, the scale is staggering. To maintain stability over billions of kilometers, each fragment would need to share precise velocity and vector alignment. The coordination implied is either a cosmic coincidence or something more deliberate. If such a system exists, what purpose could it serve? The conservative answer is purely mechanical. A body that sheds fragments distributes stress, allowing it to survive tidal forces. A comet could fracture slightly and still hold together using its debris field as a shield against micrometeorites or radiation. It's survival, not strategy. But there's another interpretation. A distributed structure allows for redundancy, multiple parts each capable of acting independently, a way to explore, to collect, to test. From an engineering perspective, it's efficient. Send one primary body to navigate a system, let smaller components do the close work. In science, we call them sub-satellites or autonomous probes. In imagination, they become something else. If 3I Atlas released something smaller, we may have already seen it without realizing. Some researchers have pointed to unexplained transient events in telescope archives over the past few months. Brief flashes near the path of the comet, micro-objects appearing for seconds before fading from view. Most were dismissed as random noise, others might be unrelated debris. Still, the timing aligns too neatly to ignore. Each flash appeared along the calculated trajectory of 3I Atlas, each moving in the same direction. Could these be fragments from the object's surface breaking away naturally as it warms? Or are they smaller bodies travelling in formation, each performing a task we can't yet measure? It's a question of perspective and of scale. At tens or hundreds of meters across, such fragments would be invisible to all but the largest instruments. They could pass between Earth and Mars and never register in a wide-field survey. Even a handful of them could change the story entirely. If 3I Atlas is a system rather than a solitary wanderer, then every assumption about its origin must be rewritten. It would mean we are not observing a single interstellar object, but the remnants or components of a larger structure, one that fractured deliberately or naturally long before it entered our neighbourhood. Avi Loeb has suggested that the behaviour of 3I Atlas fits a pattern we've seen before, though on smaller scales. He references the curious stability of Oumuamua, which also resisted acceleration, and the perfectly balanced composition of Borisov. Each was an outlier. Taken together, they might form a sequence, a statistical whisper, that interstellar space is populated not by random shards, but by entities shaped for travel. It's still conjecture. The distributed system hypothesis doesn't break physics, it only stretches it. But if 3I Atlas did release fragments near Mars, those pieces would now be moving inward, following similar paths, their separation widening with distance. In a few months they would cross near Earth's orbit. If any of them reflect sunlight at the right angle, we might detect them as transient points, bright for seconds gone in minutes. Some researchers are already looking. Survey telescopes have been tasked to scan the inbound path at twilight, the region of sky where comets are easiest to miss. The search is cautious, but the stakes are high. A detection of even one companion body would transform 3I Atlas from a mystery into a phenomenon, a system whose nature we might never have guessed, if not for a green flash in the Martian sky. For now, we have models, probabilities, and an uneasy symmetry. A massive metallic object moving with deliberate precision. A near pass by Mars at just the right distance to observe or to deploy. And a silence from the data archives that only grows louder with time. Every orbit tells us, most are stories of gravity and chance of things flung outward and lost, but some feel written with intent. Atlas glides through space, as if following a script older than our instruments, older than our language for wonder. If the distributed system hypothesis proves true, it means we have been watching not one traveller, but many a family of wanderers crossing our sky. Mars may have been the first checkpoint, the place where the story began, and if something smaller was released along the way, we may have already seen it without realising. Every orbit has a moment of invisibility, a point where geometry hides truth. For 3I Atlas, that moment is now. As it sweeps around the inner solar system, it slips behind the blinding glare of the sun into a zone where no telescope, no radar, no camera can see. For the next 3 weeks, it will be lost to us. This is not unusual in celestial mechanics. Every planet, every comet, every spacecraft experiences a period of solar conjunction when the sun stands between it and Earth. But most objects are predictable, and when they vanish, we know precisely where they'll reappear. With 3I Atlas, certainty fades. It's travelling fast 60 kilometers per second, and even a tiny change in velocity at a barely measurable thrust could shift its future position by hundreds of thousands of kilometers. And yet for 3 weeks no one can watch. Astronomers call this the blackout window. During conjunction, radio signals are drowned in static, optical instruments are overwhelmed by light. The sun becomes a curtain across the sky and everything beyond it is speculation. We can only run simulations hoping that reality stays close to prediction. In this darkness, imagination takes over. For most of its journeys, 3I Atlas has been almost unnervingly cooperative. Every observation has confirmed its trajectory, its stability, its strange chemistry. But nature loves to break patterns when we stop looking. As it disappears behind the sun, the question lingers. What happens when no one is watching? If it changes course, if it fragments, if it releases more of those faint companions some believe exist, no one will know until it emerges again. In that silence we are blind. Avi Loeb once proposed a simple way to categorize our response to objects like this. He called it the Loeb scale, a tongue-in-cheek metric from 0 to 10. 0 is pure confidence, it's a comet, nothing more. 10 is pure panic, it's not natural and it's coming for us. Most things in space sit safely between 1 and 2. Meteorites, asteroids, even interstellar debris, they are routine. When Oumuamua passed through Loeb, placed it at a 3. Too odd to explain easily, too ordinary to prove extraordinary, he said. With 3I Atlas, he nudged the scale higher to a 4. Too strange to ignore, too normal to prove. That's where we stand now, a 4 on the cosmic uncertainty meter. Not alarm, not dismissal, just tension. The kind that keeps scientists awake and dreamers wondering what they might wake up to find. In these weeks of silence, observatories will aim their instruments elsewhere. The sun dominates the sky, the object hides in its shadow. We wait for November, when 3I Atlas will emerge on the far side, visible again in the dawn twilight. Until then, we live in the gap between prediction and surprise. Behind the sun, physics still applies, but observation doesn't. The calculations say it will follow its curve swing through perihelion and head back out into deep space. But those same calculations depend on constancy, on the assumption that nothing changes. If the anti-tail we saw earlier truly behaves like thrust, even a fractional adjustment could alter everything. A 1-degree shift in direction applied at the right point in orbit could divert 3I Atlas by millions of kilometers. It could move from a safe flyby to a new trajectory, closer, slower, or even bound. These are mathematical hypotheticals, but they're the kind that make scientists double-check their models. The blackout is an uncomfortable reminder of how dependent we are on visibility. Space feels predictable until the light goes out. Then we remember how fragile our understanding really is. The interstellar path of 3I Atlas intersects our solar system in a way that's both elegant and eerie. Before it vanished, it passed within a fraction of an astronomical unit of Mars, the first checkpoint. When it returns, it will align roughly opposite Earth's orbit. Between those points lies the one place where our instruments fail, the glare of the sun itself. It's almost poetic, as if the universe planned an intermission. For 3 weeks, no one can see it. If it changes course, no one will know. In that stance, astronomers watch the sun's edges for any sign, a faint brightening, a trace of dust, a whisper of radiation. So far, nothing. The solar wind hums as it always does. The corona blazes, and somewhere behind it the object continues its invisible flight. If all goes as predicted, 3I Atlas will reappear at the start of next month, faint at first, then brightening as it climbs back into view. Its path will be checked, its motion compared with the model. If the lines match, the world will exhale. If they don't, every telescope on Earth will turn to the same point in the dawn sky. In the meantime, the blackout remains total. No data, no images, just the mathematics of expectation running forward in silence. Space agencies know this rhythm well. They wait. They prepare for recontact. But there is a quiet unease that this time the story might not pick up where it left off. Because 3I Atlas isn't just another comet. It's a visitor that already broke the rules of chemistry, mass and motion. And now, for the first time since its discovery, it has the privacy to break them again. When it returns, we'll see if it obeyed our predictions or rewrote them. For now, it rests behind the sun, a green ghost moving unseen through firelight. Too strange to ignore, too normal to prove. When 3I Atlas slipped behind the sun, it took more than light with it. It took certainty. For 3 weeks, the object is beyond reach, too close to the sun's glare for any telescope to track, too far for radar to ping. In that time, the scientific world can only wait. NASA waits. ESA waits. The amateur astronomers who first noticed its strange green glow wait too. The great machines of modern science, Hubble, Webb, the Deep Space Network, are all silent on this one object. The blackout is total. Every prediction says 3I Atlas will reappear. Every model agrees on the where and the when. But prediction is not proof. Space has a way of humbling our confidence, and this visitor has broken every rule so far. At the Jet Propulsion Laboratory in Pasadena, the orbit tracking team runs the simulations over and over again. The numbers are still, the uncertainties shrink to almost nothing. On paper, 3I Atlas will emerge right where it's supposed to, near the sun's eastern limb, visible just before dawn. But the engineers know that small errors can become large surprises. One variable out of place, one unknown force can rewrite the future. Across the Atlantic at the European Space Operations Center in Darmstadt, Germany, another team is running the same countdown. The ExoMars Trace gas orbiter Mars Express and JUICE, the Jupiter Icy Moons Explorer, have all recorded brief flashes of data from their instruments. Some of it will take months to process, compressed and relayed through deep space links. The most valuable observations, spectroradiometry, long baseline imaging, are scheduled for release no earlier than February 26. That is when the raw files will be decoded, calibrated, verified, and made public. Until then, no one outside the agencies knows what those spacecraft actually saw. For now, only a few fragments have leaked into the scientific rumour mill: a spike in ultraviolet flux, a trace of unusual polarization, a thermal signature that doesn't quite fit. Nothing confirmed, nothing denied. And so the countdown continues. In the forums and observatories that once buzzed with analysis, the tone has changed. The debates have quieted. The amateur community, which lives on open data and public access, finds itself staring at an empty sky. For weeks they watched tracked, recorded. Now there is nothing to see. The object is gone, and so is the sense of participation. It's a peculiar kind of suspense, the kind born not of noise but of silence. The world of astronomy is used to looking outward. It's not used to waiting. Every day brings the same ritual. The sun rises, the screens stay blank, and the question lingers. What will we find when it comes back? The wait has a rhythm like a heartbeat stretched thin. Scientists check the heliocentric coordinates, the Doppler shifts the predicted reappearance date. December 12th, give or take a day. That's when the first ground-based telescope should spot it again. The calculations are solid. They always are until they aren't. Even the smallest anomaly could shift the story. If the object has changed direction even slightly, its reemergence will happen later or earlier, or not at all. A delay would mean a deviation. A deviation would mean something acted on it. We're in the dark, literally and figuratively. The silence stretches across the globe. Data centers hum, radio dishes sweep the sky, instruments wait in standby. The Webb telescope will not look again until the object is clear of the sun's glare. Hubble is constrained by its orbit. Ground-based observatories wait for night skies free of solar interference. Everything is paused, suspended in anticipation. Even the language scientists use changes during this kind of waiting. Terms like nominal trajectory and expected reacquisition creep into reports. Words that sound confident but hide uncertainty. No one can say with absolute conviction what will happen next. And yet hope persists. Because if 3i Atlas emerges right where it should, it means the models work. The universe remains predictable and the mystery can return to the realm of science. But if it doesn't, if it comes out late or in a new position, then something extraordinary has occurred, something no one accounted for. There is a tension in that possibility, a quiet thrill, hidden beneath the patience. Scientists won't admit it, but waiting for the unknown is what drives them. Every blackout, every silence, every gap between observation and reappearance carries the potential of discovery. Still, the days crawl by. The countdown ticks closer to 0. When the sun moves far enough, the first telescopes in Chile and Hawaii will begin their searches. If the models are right, 3i Atlas will appear as a dim green star low on the horizon, barely brighter than magnitude 12. Within hours, that faint speck will be confirmed, catalogued, measured, and the blackout will end. If it doesn't appear, if the sky stays empty, the questions will multiply faster than answers can contain them. For now, the world waits. Scientists, enthusiasts, skeptics, believers, all united by the same ignorance. Somewhere beyond the sun, an object from another star moves in silence. It carries its secrets across the light barrier that blinds us, and until it returns, every explanation, every theory, every hope remains suspended in darkness. The last words of the daily reports are always the same: no contact, awaiting reacquisition, 3 weeks. That's how long it will take before we know whether the story continues or changes forever. We're in the dark literally and figuratively. If 3i Atlas is natural, then it is the strangest natural object ever observed, a comet that rewrote the chemistry of ice, the behavior of dust and the statistics of chance. But if it isn't natural, if against all odds it was made, then the story changes completely. It would no longer be just an astronomical event. It would be a philosophical one. Human history is built on moments when the universe expanded faster than our understanding. When Galileo pointed his telescope at Jupiter and saw moons orbiting something other than Earth, he realized that the cosmos was bigger and humanity was smaller. When Copernicus displaced Earth from the center of creation, he didn't just change astronomy, he changed identity. And when Apollo 8 astronauts turned their cameras homeward and saw our planet hanging in darkness, the image rearranged our sense of belonging. Each revelation pushed the horizon of meaning outward and forced us to look inward in new ways. Atlas could be another of those moments. If it were proven to be artificial, if its stability, its metallic vapor, its deliberate trajectory were the result of intention, the discovery wouldn't destroy science, it would complete it. For the first time, we'd have evidence that intelligence is not unique to this small blue world, that creation and curiosity exist elsewhere. It would be proof that we are part of a wider pattern. The implications would reach far beyond astronomy. every belief system, every economy, every philosophy that depends on human centrality would have to adjust. Avi Loeb once said, "Markets wouldn't crash because of fear, but because of meaning." He meant that our deepest assumptions, the value we place on progress, on faith, on purpose, depend on the idea that we are the makers of our own story. The instant we're not alone, that story changes. For scientists, it would be the greatest discovery in history. For governments, perhaps the most destabilizing. For ordinary people, it might be something quieter, a realization that intelligence is not rare, and that survival may depend on understanding, not dominance. And yet even that possibility carries humility. Because whatever 3i Atlas is, it has already demonstrated what we struggle to achieve: patience, precision, persistence across light years. If it is natural, it teaches us how little we know about what nature can do. If it is not, it shows us how much is still possible. Either way, it forces us to think differently about our place in the universe. There is a poetic irony in all of this. For decades, humanity has been sending signals outward, radio waves, mathematical codes, encoded plaques on spacecraft, hoping that someone somewhere might notice. But what if the response has already arrived, not as a transmission, but as a presence? What if while we were listening for messages, we were being shown one instead? Such questions aren't about fear or fantasy. They're about perspective. The cosmos has never been silent. We've simply lacked the tools to hear its full range. If 3i Atlas carries meaning, it may not be a message in words or intent. It may simply be a reminder that intelligence once born tends to wander. As the object moves beyond our reach, once more fading into the distance, the excitement will fade too. The debates will settle, the data will be archived, and the story will become another chapter in our long search for context. But something will have changed subtly, permanently. For the first time in half a century, humanity looked into the void and found a reflection of itself. Maybe 3i Atlas is just a comet. Maybe it's a messenger. Either way, it did what all great discoveries do: it made us ask better questions. We've always looked for signs of intelligence. Maybe intelligence has been looking back. In the end, 3i Atlas leaves us with more questions than answers. It enters our story as a bright green mystery and exits the same way, silent, steady, and impossible to define. For months we've watched it move across the heavens, an interstellar visitor from a place we may never know, carrying within it a chemistry that doesn't fit, a trajectory that doesn't drift, and a glow that shouldn't exist. Maybe it's just a comet. Maybe it's the most extraordinary artifact we've ever found. Either way, it reminds us that the universe still holds secrets worth chasing. In a time when we measure everything, when data feels endless, and discovery routine 3i Atlas has given us something we didn't expect: mystery. Real mystery. The kind that humbles as much as it excites. It reminds us that not everything can be categorized, that even with telescopes orbiting worlds and probes sailing past planets, there are still corners of reality that refuse to be mapped. The scientists will keep studying the numbers. The data will be refined, debated, archived. The headlines will fade. But somewhere in the long tail of its orbit, 3i Atlas will keep moving. Long after we stop watching, it will continue its silent path back into the deep. Maybe it will pass another star. Maybe in a distant future it will enter another system, and someone else on another world will wonder what it is and where it came from. That perhaps is the most human part of this story. Curiosity is not ours alone. It is a force of nature, a compulsion written into matter itself. Wherever intelligence exists, it looks outward. It listens. It wonders. As the final images of 3i Atlas fade, we return to where the story began, a flash of green over Mars, a brief reflection of something vast. The red planet beneath it is silent, barren, and still, the same stage it has been for billions of years. And above it, for a single instant, something from another star crossed the frame, leaving behind only light and questions. The radio static continues. The signal fades, the music slows. In that quiet, the message of 3i Atlas lingers, not in words, not in proof, but in possibility. The universe is older and stranger than we imagine, and it is still speaking in ways we have yet to understand. The strangeness remains.